In this video, we are going to start talking about ANOVA tests, and this is kind of a detailed process. So I've decided to break this up into two videos, so that way it's easier to just kind of learn a bit and then take a break and then learn a bit. We're gonna kind of do the overview of the process in this video, and then the next video is going to be very specific on the steps. And then number two, as you've already seen from the notes, there's a lot of words on this because the process is just kind of different. So make sure you've read through the first page because I'm just going to skim through that one myself, and then I'll get into detail on the process. In fact, anything that there's like a big chunk of wording, I'm going to kind of summarize here, and then you could just read through it later. Okay, so we have I just got to double check that I did that right because I'm going to mess up later on the calculator. Aha, I did not do it right. And now it is correct. Okay, so here we have ANOVA testing. ANOVA testing stands for the analysis of variance. And so what we're going to be doing, I just got to run a check on this real quick. What we're going to be, I'm going to change the page on me apparently. What we're going to be doing is comparing means, two or more means specifically. Oh my gosh, what is that? I've like literally recorded this video 3 times now, so I'm just going to strangle this PDF. Okay, analysis of variance. It's comparing 2 or more means. Let's look at some examples of when we would use this. We're not going to do these examples, it's just when we would use it. So if we're comparing the mean time for pain relief medication to take effect, we're going to determine if it's the same for A, B, and C medication. Since there's 3 means being compared, what we want to do is determine if they're statistically the same or at least one mean is different. And that right here is going to come up. Oh, that's an underline it? Oh, okay. Not what I meant to do, but perfect. At least one mean is different, and that's going to be our alternative hypothesis in the near future. So we want to just have that phrase nearby. Again, another example, it says, the administrator wants to know if the mean age, so we're still comparing, okay, now we're on underlined stuff. We want to know if the mean age, so we're comparing the ages, we're comparing the means, is the same for, and in this case, we have 4 different situations, freshmen, sophomore, juniors, and seniors. Since we're comparing 4 things, 4 means in particular, we're going to use the ANOVA test. So it's a hypothesis test, but it only uses means, so you don't have to worry about means versus proportions. And the proportion specific one we did in chapter 11 with the goodness of fit. So this will be the mean specific one, and we're comparing multiple means. And so you're going to notice that the hypotheses are kind of similar to how we set them up in chapter 11. All right, there's 6 steps. We are not going to compute the test statistic in this video because that's the long step, but we are going to talk about the steps necessary to set up a ANOVA test. We're going to definitely talk about the degrees of freedom. Oh, actually 3 and 4 we're going to skip in this video. We're going to determine the p-value in the rejection region and then make a decision. And so the reason I wrote this out is because if you're watching this and you want to jump into some easy homework, 13.1a would be these top 2 topics right here. And then 13.1c would be these bottom 2 topics right here. Those will be pretty quick homework assignments. This bottom one is all calculator and the top one is just some vocabulary. This middle part, 3 and 4, which is 13.1b, that'll be a little trickier, and that'll be what we focus on in the next video. Okay, so step 1 is to make sure the conditions are met. So we have this scenario here, and then on the second page, we have the conditions down here. So it says a statistician wants to set up a hypothesis test to determine if the mean yearly tuition, so we're definitely talking about the mean for colleges and universities, is different in Massachusetts, California, and New York. So those are our 3 means that we're comparing. Assume the populations are normally distributed. All samples are randomly. Okay, all this stuff will help us with the bottom. So at first it says each population is assumed to be randomly distributed. So, or no, each population is assumed to be a normal sample. So this right here, that answers the first question. So that's for question one, or not question, but first condition. That's for condition one. And so we say, yes, they are randomly distributed. Check. And that's normally distributed. Now we're in random. All samples are randomly selected. And so if we're looking through the words, it says right here, they're randomly selected. That answers our question two, or condition two. So we say that, yes, all samples are randomly selected. Now, the third one, all the populations are assumed to have equal standard deviations or variances. Well, if we look at, I'm going to highlight this one because it stands out a little more. It was determined that the variance for tuition was higher in Massachusetts. Higher means not the same, not equal. So for number three, that's where we're getting the information for number three. We have to say that is not true because they have to all be equal, and this one says one was higher than the other two. All right, last but not least, 4 and 5, the factor is a categorical variable and the response is a numerical variable. Factor and response were defined up at the top of the page 1, but just to go over it, the response is always going to be whatever we're taking the mean of. So in this case, it is the tuition, which is numeric. It's something we're taking the mean of. We have to take the mean of a number. We can't take the mean of words. So as long as we're taking the mean of something with numbers, then it will be true. Oops, I'll put excellent. And last, the factor is categorical. The factor is what we are comparing. So here we are comparing the different keys, comparing different state universities. Perfect. So we got all of the, so 4 out of 5 of them met the qualifications, but 3 was wrong because it said it wasn't equal. Okay, so using the same example, we now want to set up the null and alternative hypothesis for this test. We're not going to do the test. You can't do the test because the variances aren't equal, but we can just kind of set up a null and alternative hypothesis. All right, I'm going to write this a little bit weird just because you know how fun it is watching me write muse. Actually, you know, I'm just going to write the word mu. I think that'll be a lot easier. Okay, so let's get my text up. So we have the null hypothesis, and that is that mu of, we gotta just put our states, mu of, yeah, I'm gonna write out what I'm trying to write, and then so I can model it correctly. I want mu of Massachusetts. Oh my gosh, that's terrible. So it's a mu and then subscript Massachusetts. I really wish I could type in math on this document. Okay, mu subscript Massachusetts is equal to mu subscript California is equal to mu subscript New York. So the Massachusetts, the New York, and the California are all subscripts, are all lower, but as you can see, it's just not working for me today. All right, and then the alternative is the opposite of that. So instead of they're all being equal, we want to say at least one mean is different. Now, just remember, or I don't know if I've said this before, but everything being equal and nothing being equal are not necessarily good choices for this, because those are only 2 scenarios, and we also have to consider the scenario that maybe Massachusetts is different, but maybe California and New York are equal. So we say at least one is different. So maybe 1 is different, maybe 2 are different, maybe 3 are different, but we don't need to write out every scenario. We just say at least 1 is different. Now, before we go on, just going back up here, I said we're going to come back to this. So this right here we talked about earlier, that is going to be every alternative hypothesis. At least one mean is different. It's going to be every alternative hypothesis. And then we said the means are statistically the same for here. I would say mean of A, mean of B, and mean of C are all equal. The mean of the freshmen equals the mean of the sophomores, equals the mean of the juniors, equals the mean of the seniors. Okay, this is not too terribly difficult to write because, oh, it is for me, because it'll be multiple choice on the Newton-Alta homework. Okay, next up, determine the degrees of freedom. Again, lots to read. I'm going to highlight some key points, and then you can read this all in detail later. So first of all, we're talking about the F distribution, which was named after Sir Ronald Fisher. And normally I don't go too much in detail about the person who invented it, but this is called Fisher's F distribution, and that's how it's called on the calculator. So it's important to recognize both of those, Fisher and F, so you can find it on the calculator. So what we're going to be talking about is the F-test statistic, and it is the ratio of variability between the groups compared to the variability within the groups. What that means for right now, we'll get more into, that's what we're going to get into detail in the second video. But what we need to know right now is the fact that it's a ratio or a fraction means there's a numerator and a denominator. Okay, so that means we have degrees of freedom for the numerator and degrees of freedom for the denominator, and that's what we're going to focus on here. So here's the formula. To find the degrees of freedom for the numerator, we have the formula k minus 1, where k is the number of groups or categories. It just depends on what's easier for you to think of. This is the same k from chapter 11. So whatever it got you through chapter 11, that's what k is, however many groups or categories we're talking about. The degrees of freedom for the denominator is n minus k, k being the number of groups, and then n is always the total number of things that we're talking about. So for this first problem that we're going to do degrees of freedom, the degrees of freedom for the numerator and degrees of freedom for the denominator, first we need to know k and we need to know n. Okay, so k is the number of categories. I look up here, and categories can go down or across, just depends on how the table is displayed. This one is going down. I have 4 companies, A, B, C, and D. I could see it here, or I could see it here, 4 companies. So k is equal to 4. In this one, we're talking about the total number of employees being interviewed or whatever's happening in the random sample. I'm going to add up all these employees. 10, carry the 1, 2, so this is 60. If I add all those up, so n is 60. All right, now I take that information. The degrees of freedom for the numerator is k minus 1, which is 4 minus 1, or 3. The degrees of freedom for the denominator is n minus k, or 60 minus 4, which is 56. Okay, cool. Okay, what we're going to do with all of that is we're going to take the degrees of freedom, put them into our calculator under Fisher's F distribution to find the reject region. Oh, and I changed some of this, and so some of it still says critical value. We're not doing critical values, we're doing p-values. Okay, so here we have a problem. We're going to set it up. We're going to find the degrees of freedom to determine the p-value. So to find the p-value, we need to know the degrees of freedom of the numerator, the degrees of freedom of the denominator, f, that'll all go in the calculator, and then this one just says determine the p-value, but I'll probably just take it one step further and finish the problem since we have the alpha right here. Okay, so first up, we need n and k and n for this problem. So how many categories? We have 3 medications. So n is 3. K is 3. For the number of people in the survey, this one's a little trickier because a lot of people like to say that there's 5. But notice up here at the beginning, it says for each medication, a sample of 5 people are selected. So there's actually 15 for n. 5 times 3. Okay, So now we can take that information and the degrees of freedom for the numerator, let's be subscript, is going to be k minus 1. I just like to write the formula each time so that way you can practice seeing it, which is 2. And then the degrees of freedom of the denominator is 50, it just says the formula, n minus k, which is 15 minus 3, so 12. Okay, so we have this number, the 2 and the 12, and then we have f is going to be the other piece that we need to know. We need to know that. Oh, I can't highlight stuff that I typed. Oh, look at that, I can. Apparently I can't highlight the 2, but I need to know that f, the 4.21, the 2, and the 12. Okay, so let us jump over here. Oh, I think my kids' soccer pictures are going to pop up first. Oh, that's okay. Okay, so here's it. Oh, I was already, remember I told you I made this video like 3 times already? Okay, let me just start from the beginning. Okay, so we're going to go to distribution, because remember, this is the Fisher's F distribution. If you know all 3 of those words, you can get right to it. So we have distribution, check. And then we go all the way down, Fisher's F. Perfect. We have everything we need to know. Again, all the way down on distribution. So ask for the degrees of freedom for the numerator, which was 2, and the degrees of, what did I just hit? And the degrees of freedom for the denominator, which is 12. This one uses slightly different notation. They call it D1 and D2, but it doesn't matter because they write it out very clearly in words what they're looking for. So this is not asking for N and K. This is asking for the final answer when you've calculated the degrees of freedom for the numerator and for the denominator. And now we are going to do a right-tailed test. I wrote this out, but it's a little bit later in the packet. All of these are going to be right-tailed tests. And finally, what we want to do is we want to, so remember F was 4.21, so that's like right over here, like almost like 4 1/4. We want to know the area under the curve to the right from 4.21 over. So area under the curve is the same as probability. So our p-score is going to come from this probability right here. I type in 4.21, and it tells me that my p-value is 0.04. So that means 4% of the area is filled in. All right, 0.04. I usually just go to 2 variables. It's all good. Okay, so what we determined from the calculator, the p-value is 0.04, yes, or 4%. I also like to think about it. This is nothing new. P-value is percent. That's how we compare it to our significance level. I won't finish this one because it doesn't say to. It just says find the p-value, and you're going to have a lot of problems that just say find the p-value. So we'll stop here. In fact, I'm even going to delete this because right when it's asking, this is the answer. I'm being so specific because remember last chapter 9, how is a mess with the p-value? So to avoid that, I just made up a whole different assignment for 13.1. So this is going to be 13.1C. It's going to be just like this right here. And I had to do it in Canvas, which means Canvas is a lot less generous with the answers that it takes because it kind of reads it as text. So if you write 4%, it'll mark it wrong. So that's why I deleted that. You want to put it in 2 decimal places, 0.04. Okay. So this is what we're going to skip. We're going to skip, well, I'm just going to explain it briefly, and then the stuff below it, we're going to skip until the next video. I will start here and explain this a little more in the next video. But remember I said the F test statistic is a ratio. So it's a ratio of the mean square between compared to the mean square within. We have this fraction, which is where the degrees of freedom for the numerator and the degrees of freedom for the denominator come into play. So this part right here is nothing new. We've had it in all the chapters with hypothesis tests. My dog really loud. He's like walking. They're loud right now. All right. So if P is greater than alpha, we will not reject the null hypothesis. if P is less than alpha, then we will reject the null hypothesis. In other words, up here, we would reject because P is 4.04, 4%, and alpha is 5%. We'll get into that. Okay. Skip. See how we need a new video just for this because it's very scary. So we're going to come back to this example. So did I skip too far? No. This page right here, step 6. So again, with this rule, if P is greater than alpha, we will not reject the null hypothesis. If P is less than alpha, then we will reject. We're going to make our curve. We're going to have our alpha, and then which side of the curve, which side of alpha does P land on? And I just mentioned this, but here we have it in writing. It's always a right tail test. Okay. So let us look at just a few examples of one that's mostly done for you. But I just want to go over some of the more, I don't even want to go over any of the calculations because I think it'll be scary. Okay, so what we're going to do is we're going to find F. F is the fraction 4.05 divided by 7.58. Why? Well, right now, because I said so, I said that F was this fraction right here, mean square between divided by mean square within. We will get a lot more details about these calculations in the next video. Okay, so let me just calculate that real quick. 4.05 divided by 7.58, and we get 0.534. Goes on. That's a good number to stop. Okay, the reason I'm doing that is because remember, for the what we're going to do here is we're going to finish the test. So we need the degrees of freedom of the numerator. We need the degrees of freedom of the denominator, and then we need to not mess this up. We need F. Okay, well, you know where F is. I'm not going to circle it. Okay, so we have 2, we have 11, and we have 0.534. We need to get P, and we're going to compare it to our alpha. 2, 11, 0.534. So here's our calculator. We just have to go back 1, 2, 11. Oh, this is kind of annoying because it always just goes back to left tail. I don't know why. It's always a right tail test, so why not just let the calculator force it to be right? I don't know. And all my complaining, I forgot 0.534. All right, so I am getting my p-value is 0.60. So I come over here. I'll just write it at the bottom. Actually, I'll write it at the top so it stays with this problem. So this one, we determine that the p-value from the calculator, hang on, I need to jump back here, 0.60. Okay, so we're comparing that to alpha, and 0.60 is greater than 0.10, which is alpha. So since 0.60 is greater than 0.10, it's greater than, we will not reject the null hypothesis. Okay, I'm going to go on the picture and just explain what was happening. So going back to the calculator, we have, here is, wait, where is alpha? Well, it's hard, actually, it's hard to draw on here. Let me just draw it on my lovely PDF. So we had, I'm just going to draw it up here because I have a little bit of space. Just determine where we want alpha to be. Alpha is going to be right there. So all of this right here is going to be our alpha, which is 10%. And where does 60% come in? 60% is way, this is not drawn to scale, but 60% is way more. It is to the left of our line. So over anything on that side of the line is do not reject, because alpha is the cutoff line. So we look at, I'm going to draw a better alpha. We look at where alpha is and we say where it, this is the same. I'm already repeating myself. We did this in every chapter before this, I feel like. All right, alpha. And then this is where P landed. P was greater than, was a greater percentage than alpha. So we will not reject the null hypothesis. Okay, next one, or last one. Given the ANOVA table, so this one's already calculated for us. Should the null hypothesis be rejected at the 5% level of significance? So here's my F, my 2 degrees of freedom. So I have 2, 7, and 0.38. One more time on the calculator, 2, 7, right-tailed, 0.38, yikes, 0.70 is, they're going to get a lot of really big p-values here. So we have p-value is 0.70. That is greater than our 5%, which is our alpha. When p-value is greater than alpha, we do not reject the null hypothesis. Copy that and paste it. Okay, so that's the basics. And then we will get into how to do all the calculations in the next video. Yay, isn't this fun? I know it kind of sucks that this is the last chapter because I feel like this is like the least fun that we do, but it's a necessary evil and it's in the school. All right, so I am going to stop this and make the next video, but feel free to take a break and watch it when you're ready to do a lot of calculations. Bye.